All right. Looks like most of you came back. Anyway, it's next week and the week after that. Yeah. So we're going to turn this light off again. Is that what the advanced technology? No. What'd that do? What am I doing wrong? I pushed the bottom one. Yes. The one that says off. Turns out. Is that okay? Right. Not for after lunch, right? That's when. Yeah. The trick is not to eat lunch. Lunch is obviously, yeah. All right. So what have I done? I will try to get my voice out there, and if I need to speak Australian, I will. I'm not going to do it. Okay. Let's see. So things that, lots of little glitches, of course, in the first week. Maybe that doesn't happen in other classes, but mine is a bit of a lumbering beast with wheels coming off in different directions, because that's what happens narratively. There's always a flaming wheel comes out somewhere. So let me make that a bit bigger. Yeah. Okay. Yes. There'll be Highlander references, but you probably shouldn't watch Highlander. You should just know that exists. So there's now a little story section, which will be about what happened. Ooh, yes. Spoke. See, I can adjust, right, depending on what I want to show, right? So this is advanced. Yeah. I don't know why I do these things. So there's another spoon at home. So I'm going to try to keep things right. So we're recording, hopefully. I fixed a few things in post, which, if I did that properly, would be to delete the whole thing. But anyway, so we'll have the slides. Obviously, I've misspelled this. I'll fix these things up and make it automatic. So there's a little description, and then there are assignments. So you can kind of come to this. This will be what happened, because that turns out to be a hard thing to remember, right? I wrote a paper on that in the last couple of years, trying to explain what happened, which is in the second volume of Pucks. Because it can get a little tricky at times in history. All right, so this is just going to kind of fill up and populate. The instructions will, be fairly simple, I think, but usually you should be able to come here and see which assignment is up. We have office hours after this. I think it's 11:45 to 12:15. I set it up on Teams, so you can attend by Teams, and I'll, write so that things go through. I mean, you should be able to see, where's that little, oh yeah. This thing, right? So you should be able to sort of interact like that, and we'll try to handle it well. It's a small assignment, so it's just a half hour. If you want to come in person and share in the COVID, then we can, then that's, my office is on the 4th floor of innovation, right? There's discovery and innovation, which are terrible names. It should have been, trial and error, or everything is on fire, and why did I do this? Don't touch that beaker, something like that. But discovery and innovation, which, anyway, I don't know. Yeah, what a tragedy. Also, I discovered there are really no chairs outside of that building. Like, there's a whole quad thing, right? Yeah. Anyway, I complained, and someone said it was a good idea, so that's as far as that will go. But anyway, because money will get involved at some point. But hopefully we should have some tables and chairs because of humans. All right. So this is sort of coming along. The little Pucks of Vox thing. Well, Vox of Pucks will tweet away here. It's got lots of fun little things. Anyway, so you are welcome to look at that. And the extra piece there is, you don't have to go to Twitter if Twitter is a horrible thing to you, which is fair enough. Then you don't have to go there, right? It just sits here, and it's mostly links to interesting things people have done. Benjamin Schmidt, for example, is head of the digital humanities thing at NYU, and he does lots of interesting things. I think some have blown up, but they're like narrative arcs of The Simpsons and all sorts of stuff. This is about basically where everyone is in the US, which is sort of interesting. And obviously terrifying, etc. Yeah. Okay, good. So I have a list of things to do. So assignment 1 exists. I put in the right place. We actually have a syllabus, so that's in the more things section, right? So this is just extra stuff, which may be more or less a bit of a mess, but I I said, you're right. So Michael Arnold, you'll be able to contact him on Teams. So Teams is functioning more or less. I'll go to that in a second. And I got that. There are 5 or 6 people who are just doing this online, sort of in person as well. But they weren't automatically in Teams. Anyway, mess. And Blackboard was a mess. Blackboard exists, I think, now. And Michael should be involved. So Blackboard should be okay, and we should have some material on there, like where to submit the assignment is essentially the most important thing there for Blackboard, right? So that's how we're using Blackboard as a place to submit things, right? Also grades. Okay, so there's a little, if you want to look through this, you can. I guess I haven't updated it to, apparently SEMS now has one that's like, there's a base amount of material that you have to add, which is like 15 pages or something. Maybe some of you have seen this and other things. I haven't done that, but it does feel like we're getting to a terms of services Apple situation, and then it's a South Park episode, right? So we don't want that.
Can you say a little bit about how we're working together on assignment policies?
Oh, yeah. So, I want you people to work together. I mean, if you want to do the lone wolf thing, that's fine. But I think we're in, I like people working together. Obviously, I don't want you to just copy it, blah, 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 all those things, but you should work together to figure things out. So, if you can find, I know it's, right, you have to somehow meet each other and so on, but if you can group together and be kind and good people, then that's a good thing, right? So in years past, we've had really nice, there's one year where the group all went out for trivia nights together, like the whole thing turned into some sort of animal, and they would sit outside my office, and one would be sent in for a question, and then they'd run back, and it's like a horde of them. You don't have to do that, but I mean, you guys are you guys. So, no, but please work with other people. Yeah. Office hours are generally very useful things, right? I'm involved, but usually, we'll work through things. The questions in some of these assignments, they're sort of, I know I have this in the overview, which I'm just going to put back, but they're kind of researchy sort of things. They're a little in between, right? So this is different from stuff where it's like, oh, here's calculus, here's a billion things, just learn. There's maybe some narrative arc, not like linear algebra, which is a beautiful story of the matrix. But when you get to sort of some of these higher level, you should. There's just weird problems, and it may be that you need to stick a bunch of tools and ideas together, and then we're getting more into what research is like. So that's it. It's a bit of a transitional thing into research. All right. Okay, that exists. Talking. Yeah, so Blackboard, as I said, that's a merger of 4 classes. So that was kind of, because there are 2, the CSIS and math, and then the online version. So amazingly, it didn't seem to explode, but it was a bit slow. So sorry about that. I know these are hard to read, and this is really for me, but we're going to move all the research papers that I cite. They're going to be on the Silk server, so that's a detail for me. Okay. Please do try to contact me or Michael through Teams. Email is a hellspace, and everyone should be arrested for using it, but it's still there. It is it's where admin lives. I think they only send small emails around all day. Anyway, we have work on how organizations work, and anyway, all right. But try to contact in Teams, and let me get the Teams thing up. So Teams. So here's our little channel. It has a fish. The fish will be explained, maybe. Anyway, so there's a general, right? So if you come in, the first place you get to, there's this general one, which will be just sort of a sequence of posts. I don't think files is anything. So this is, we'll see how long I keep this up. This is a stream. This is the Microsoft streaming service or whatever it's called. What they call it? They just called it Stream. Anyway, so I'll sequence them there, but I'll put them on YouTube as well. YouTube is better. So there's going to be a big playlist for the whole thing. And then the course website can live in here as well. So in principle, I guess you could just stay in Teams, right? Like, okay, yeah. So if you only wanted to live in Teams because you really think Bill Gates is a champ, then you can do it. He's not. Okay, so so assignments, just pile questions in here. I realize there's a student's question, but these are open, right? So you guys should Projects, videos we'll put here eventually, and projects we'll get there. And if you have questions for office hours, that's a good place to throw them in. And I'm happy to add other things. Oops. Is that everything? No, I'm in the wrong spot. It's not the worst, but it's, yeah. Anyway. Okay, so the machinery is sort of building up. Okay, and there was a question about, do you have to watch all of these videos? Yes. No. So please don't do that. That would be painful. So, if you go to something like this one, right? So they're all the little clips. So maybe for some reason you want to go back and look at these things, right? Then they're there for you to kind of easily get to. That was the idea. They're from seasons past, right? This is the 16th season. So some stuff I will, tell untruths about, or it will change and so on. But yeah, right. So that's a historical documents for your, to help you out, right? And of course, it's just open online because I want to provide things online. Let's see. Yeah. Okay, so the instructions will tell you what to do. And if we've had online versions, it will be, watch these clips or something. And they're not there, they're not there. So I guess it's on me. If I don't put the thing in here, then you can say you didn't tell us. Okay. All right. So Teams exists. We've got the YouTube page. All right. So let's talk about some things. And I usually like to, add some interesting things. And of course, they're going to be generally bad this year. There's a COVID outbreak. Just saw this morning in a nursing home in Windsor, Vermont. Yep. 30 people. I guess no one has died. People are sick. But it's just stupid. We're just stupid, And anyway, so hopefully no one does. But the numbers are, yeah.
Essex County, New York reported a nursing home just this morning in a vaccinated patient.
Oh, Essex. Okay, yeah. Because Essex is the Northeast Kingdom here, isn't it? You're over the right. What's your congressman again? It's Elise Stefan. Yeah, right. Represent. Okay, so well, I'm very sorry to hear it. Yeah. Maybe I said this the other day, but I come from rural Australia. My mother is 79, and she just got her first injection. Right, she just got her first thing. So this is a first world country. Yes, by the way, it is. And same with New Zealand, but just the vaccine. It's a big, complicated thing how you respond to a pandemic. I guess the best thing we've done is absolutely the vaccines, and in some cases the rollouts have been very good. Vermont did really well, but places like Australia and New Zealand have messed that part up, and Delta is taking hold. So we'll see what happens. But you do have a population that is definitely exposed. All right. Okay, so I wanted to throw this in here. This is something I'll talk about at the very end of the course again, but I want you to. I feel like sometimes I should put it at the front. Okay. I just want to say this, right? So I find that when I listen to people, I don't know. This is my boiling down of science, right? So find interesting things to work on, right? This is quite difficult, and that's sort of the zero thing, I think originally when I wrote down these rules, I didn't quite, rules. I mean, came up with these things. I didn't have this there. It was sort of taken as read, if you like, right? So this is hard because it's up to you, but it's also up to your whole environment. Who's funding you, what your advisor who's still doing the thing that they did 30 years ago and should stop. What they think is still motoring along. But that's complicated. And we're in this Renaissance time in science. I mean, I may say that more than once, but that's where I think we are, right? The last 30 years with the advent of the internet and then everything that's come after that, good and bad things, but it's really, it's completely different as to what you can do. I had a sociology chair explain to us that the internet hadn't really changed anything. Just more data, just things are a little bit, it's just like a little bit of, come on, study the sociology of the internet. It was Bongard and I were on this thing, and we're just, anyway, okay, people. All right, so taste. I want to use this word taste, right? So this is my advisor, Dan Rothman at MIT. I remember talking to him about this. And, I think even after I graduated, years after that, it was really, it's interesting. It's a bit of it's dangerous to talk about culture and, because you can, make a mess of things. You want things to just go well without, but taste matters. And that's a weird thing to say, but I'm going to put out that there's taste in science. And that's, from you reading lots of things and exposing yourself to lots of things and seeing and getting a sense of where things went wrong historically as well. And they will. Science will do that. That's okay. But it's a little sad to find yourself out on the end of a plank and you realize that you've added a lot of planks and there's nothing out here. But So, but then these are the basics. Describe what you see and explain it. So this is basic science. Describe and explain. And we have this on the Vermont Complex Systems Center thing. I think it's important. So the other day there was a discussion. I'll stop blathering about this. This is professors talking about how data science and AI are basically the same. We could just merge those degrees together. I'm quite serious, and I'm just like, no, And so data science is the thing that will help us, stop AI from killing us all, maybe, right? But AI is very smart, so it'll figure out how to make data science not work. But data science is just in the great tradition of science, right? It's a forensic thing. You're trying to, first of all, describing is hard, and it gets a lot of, I think it gets short shrift, basically. Instrument building traditionally is of course the essence of science, right? Like measuring and instrument building. And it's all bound up. These things go back and forth with explaining, right? You toggle back and forth. You toggle around all of these things because you realize it's not meaningful or whatever. But then you can do all these things we want to do. And this is where, say, AI lives, right? Replicate, predict, control. But, this part gets unlocked. And often we're floating around in here and doing stuff, and then we get the science to work as well, right? Like, how does a baseball work if you throw it? Really boringly, actually. But sorry, that's the game of baseball. Anyway, so I'm happy to talk about sports. But this is, it is a bit of a smushing around. But when we get the science to take hold, we're really trying to get this to work. And then we can say, yes, the big test, obviously, is prediction. And we've done so well with that we were in this kind of odd age, I think, of people being like, oh, you must be able to predict the next terrorist attack or the next whatever, social. It's going to be easy, right? This is obviously the hardest thing to do. I mean, Asimov has his psychohistory and it's all, which is statistical mechanics. It's basically, balls bouncing off each other. If you look at what he said, I mean, it's a bit fuzzy, but it's incredibly hard to measure. And social phenomena is, I think, we're going to sort of show, we're getting there. We're showing that it's really hard to prove. We can understand that we can predict the weather for 14 days max, and that's it. It doesn't matter how much better our instruments get or our data gets. That's a limit, and that's incredible understanding. Anyway, so what happens tomorrow with humanity? Well, yeah. Right, and then sharing and do all these things. So, and I want to just have this at the start. I'm going to talk about tools and models, and they're important historically, but we're still stuck a little bit. It's always true where people will just keep using the same things, right? So you want to sort that out. Some of them are very important to know about, but that doesn't mean you march out into the world and say, everything is this shape or whatever. It's this system. And we'll try to sort of sort that out as I go through it. All right. So again, I've done this go to the end thing, but I think it's a good thing to do. All right, so I think that's good. Koalas are stupid, just so we're clear. Good thing is they don't even know we're saying that. Okay, so I think I was going to show you this. So the paper is, this will connect into what I'm talking about scaling. This is just a big outside structure. It's PNAS 2018. I mean, I like critiquing, papers, how they work. I mean, this is a reasonable title. It doesn't say you went. It doesn't. The worst titles, I'm going to say, these are the ones with question marks. That's a huge no-no. We're scientists. We're not it's not a mystery. Is the Earth going to explode? Question mark. Just tell us in the title, you idiots. But people have a real fetish for that, and they'll be like, no, everything has to be a question mark. we have one paper that has a question mark, but then the answer in the title, like it goes straight after it. Um, there was an argument whether I could put a semicolon after the question. I really wanted it. Anyway, so this says what it's about. It doesn't tell you where we're going, right? It doesn't tell you a story, right? I mean, it could be chickens, like, and then, it's a little more than that, but it's, it's a measurement of, right? And I will critique these plots. These are terrible plots. I mean, this just, I don't know why they chose this. It's okay, but this is, an effort in terms of measuring carbon to try to, figure out, and it's cubic gigatons, which is a lot. But plants are the big deal, right? So plants are dominant. Viruses are hanging out in this tiny little piece here, but they, these little locks and keys have a lot to do. Of course, they're considered edge of life things, right? They're not really alive, but they interact with life, kind of like professors, right? They're in that sort of category. Anyway, bacteria is over here. Fungus, we've got the funguses among us. But animals are this little chunk. I mean, and again, this is a terrible plot. I mean, just simple bars in order would be much better, right? So, it's an F. What's it? Well, because you can't. So if you have something like the US, right, and you have something for all the states, it's very important, I think, to have the map and the list. Because you want the ranking, right? And you want the map as well to see if there's geography. This is a different kind of game, but I think it has that same sort of thing. We'd like the list. There's no, like, what is this boundary? Like, why is this? This is, we're just putting it in a thing. And they're triangles as well, or polygons, actually, which is a bit quirky. So I mean, it's fine. It's not a lot of data. Oh, brokerage, yeah. Oh, do you mean like they're called tree maps? Is that what those names always? They don't look like trees, right? Yeah. Well, then this one, for example, gets scaled up to a square, so it's like, so this is a no-no. But anyway, the information is kind of there, right? So, but animals, small chunk, right? We're in this box. And humans are over here, humaning. We've got the wild mammals, got them on the run. Well done, people. And we've made ourselves some things to eat over here. Fish, hanging on. Wild birds, not so much, right? So obviously, it's a hard thing to count, and there's some pretty, this doesn't have any error bars on it. That would be, again, if you just had bars, you could have some nice big errors on it. So of course, this was sort of sitting there, and I think gave people, who like to do visualization, which I do too, but I'm, like limited. This one's a little, they've reluctantly pulled out a bar plot, but this is now this is, terrestrial versus deep, and so that's a little, breakdown there. I mean, you can see there's only three things, but then where are they, right? So plants are terrestrial, fungus is up here, archaea is down below with the bacteria, which gives rise to stories. Anyway, okay. So they're their sort of main plots, and it's a good piece. And then, so people, of course, came along and just said we can play with that and make some fun things. Let's see. So this is, this is another version of it. So now we're into the plants. So just stacked. Each one is a gigaton of carbon, each cube, and then bacteria is down here, and then plants. You're like, okay, plants. Okay, plants. And then we've got this little offshoot here of the animals, and the humans are up top. And then we'll go into that. Arthropods, so this is, I mean, I guess it was on the other one. I didn't quite see it. But arthropods, solid. And the fishes and the mollusks, they're doing pretty well. Nematodes, always got nematodes. And then down into wild birds for some, anyway, it's just, I guess what they wanted to show here is this is 2,000 cows. I mean, this is a huge, I mean, you make fun of this forever till the cows come home, as it were. But like in England, everything's measured by double-decker bus lengths or heights or whatever, or milk containers or something. And or football fields, and no one really knows what it means, but it's sort of fun to say. It's like 500,000 football fields of, you know, desert were something, right? Anyway, so they tacked that on. So that's not a bad one. And then I thought there was one more. It's interesting the way they did it. Very animal centric, right? So we'll go for animals. And they give you some little visuals here. So the arthropods, the king crab is king, and then we've got some fishes. You know, so you can sort of get a sense as you come down what they are, the humans sitting here. But actually, it's a bit deceptive, right? Because this is that little stack in there. So you can see, I mean, if we were the octopuses, we'd front the octopus one. But so this is description, right? This is a hard thing to do, and it's useful, and it might be off by a fair amount, but this is a good anchoring to have. So what's not in here is how all these things fit together, right? Who eats whom, right? There's a lot of eating of whom's. Many whom's are in the being eaten category. And so that's the food networks. And of course, how do animals interact with plants and also environments. So there's a much, this is you have to do this. It's very important. It's an accounting thing. But then there's some huge network fabric structure that we would like to investigate. And that will be hard to get to. But part of seeing how these things fit together is, is going to be the scaling story. As you go up through orders of magnitude in life, how do these things use energy? Like, what are the variations there? So that's going to be a slide. I have a Sandbox for slides. It's called Sandbox, but it's got 20,000 lines in it, so it's not a very good Sandbox. Okay. I recompiled it, so it died. Adobe, you're so bad. Adobe, so scared. It's a mysterious thing, Adobe. Just hanging out there with the PDFs. Okay, so let's get back to the koala. Okay. So scaling, and just to will this go back? Yeah. Just to go back quickly to this big figure, which was great. Sorry about that. Yeah, this one. Right, so as I sort of presented the other day, many orders of magnitude here. This is very satisfying. So what's a reasonable amount of scaling? So then we'll just start with that point. That's a very important thing. And there's sort of 3 orders of magnitude. This is, just humans saying to other humans what they think is a reasonable kind of range for which scaling is persisting. Lots of argument about whether something is really scaling and so on, right? So there's a description. Of course, you have to explain it, right? So there's a lot of people have a lot of trouble with the description part. But in the end, we have to explain, like, why is this scaling coming about? And, maybe the one that you've measured is basically right, but it's off. Yeah. So you can have this where you have one variable scaling, more than 3 orders of magnitude. The other one maybe not so much. Depends if it's a dependent or independent one. And then, you get these sorts of plots appear in nature and science. We've maybe gotten over it a little bit, but you'll see these plots and they're like, oh, we have a scaling, blah, blah, blah. And I'll show you a little bit rough. So this is from a much larger body of work, and I don't want to impugn that by just saying about this one, but this plot is not great. This is from Betancourt's work, and that's later in this set of slides as well. So Louis Betancourt, who's at Chicago now with my old friend Neil Brenner, they work on scaling with cities, right? So whatever properties you can come up with. Lots of debate about whether you can do that well, and density and all these things. But this scaling, this is so first. Well, it's natural log, which is chunky. Shouldn't be doing this, right? So this should be log 10. Where it's not a mathematics thing. But right, we've got a line. There's a R squared is not bad. The slope is 0.093 though, right? So this slope is basically 0. I mean, you wouldn't want it. I mean, a 0.1 is very thin. We'll see an example of where we get something that's about 0.1. that seems to be actually real, but again, not much of a range. But this is walking speed in cities, right? So this is this sort of I don't know, sort of 100 years ago kind of behavior where you go around and just some statistician called Pearson or whatever counts what people are doing and assesses them, and they look at how fast people walk around. Now, of course, we can do that a little bit better and better with people tracking in non-invasive ways, right? Of course, I'm joking. Phones, smartphones, you can track how people move around. Again, for good and bad, but do people walk faster or slower in Dublin versus New York City, right? That's sort of the game, yes.
So, okay, I get why the small variation in the dependent variable part, why that's a problem.
Mm-hmm.
But what is bad about natural log versus log-based 10?
Yeah, no, this is just a contract between humans that log-based 10 for talking about scientific observational things is a good, and it's it's a communication thing at this point. So, all through engineering, and again, we could blame the French for a lot of things, right? But that's a nice statute. It's okay. But we adopted it, and that's what we're kind of doing. And if we were happy with this, or 12s or whatever, then we would do that too. So if we had a dozenal system, then we'd be, maybe 3 orders of magnitude would be 12 times 12 times 12. That would be okay as well. So it's just a communication thing, right? Just as we're using the same words, right? From a meaning point of view, I think it becomes that. And it should be log 10. Because you have to convert this. You're like, okay, well, 2 of these orders is about 10. So this is actually, this looks, 10 orders of magnitude, right? It's not really that true. So very weak scaling, a fun thing to look at, but, the idea that this is really a power law scaling, right? It could be, there's lots of things that could fit this. It doesn't have to be, y is proportional x to the alpha. All right. So scale invariance is a term you'll hear, right? And it's obviously in the world of fractals and so on. This is often used. Depends who you're talking to. There are some old grumpy people who don't like using the word fractal, and they'll just talk about scaling and so on. Objects look the same if they're rescaled. So that's a big question of any system, right? Do small companies scaled up in the right way look like big companies? Do small towns scaled up in the right way look like big cities? What holds up, what doesn't? If you take a mouse and you scale it up to be an elephant, obviously it still looks like a mouse, but is it kind of, things about how much energy it uses, how tall it is, and so on, do they hold up? So lots of things, so I'm talking about shapes there, but it could be time series. So finance, for example, is full of these things, but signals that we get from the Earth, right, like the seismic measurements and so on, lots of fractally things like that. Okay, so lots of things in the world can have this sort of scale invariance, and it can be statistically the same, right? So there's some wobbling around. It's not, you don't make it doesn't look exactly the same or exactly the same, but it's got a typical shape. So rescaling, we're going to just change the units of measurement, right? We're going to zoom in, just change the units of measurement, and so there are many things in the world or many systems where we can kind of move through all these scales, and if we do it in the right way, we can replicate components or sort of views of the system at different levels quite well. It's not always true, right? So, but we're focused on where we can find scaling. So we've got our simple little thing, right? This is just a general relationship, some power relationship. And if we rescale them properly, right? So we're going to change to another unit of measurement, for example, and maybe we go from meters to something else, then we'd have to change y in this way. It's just a simple thing. I'm just going to put in, y is, right? So we're going to replace it with this rescaled version. This is our new dimension here, and we'll replace x with this rx prime. And we've chosen this, this r, we did the thing first, right? So this would work. So there's an r to the alpha, an r to the alpha there. These things are going to cancel each other. And we've got the same form, right? So it's the same form. But we had to change we couldn't, it's not isometric. We couldn't just simply change y and x in the same way. All right, so I'm not trying to, this is not anything crazy, but it just builds out from here. But if you take something of, any other function basically that's not of these parallel shapes, then, like this is an exponential, it has ways of being, you can look at it and we can think it's sort of the same thing. But if we try this, right, there's no way to extrude if we put in our, we change to a different scale here. There's no way to kind of extrude this out, right? We can't do that. So we've changed the form. Okay. You'd have to actually scale. You can't rescale y by some power. You'd have to, if you do y to the power of 1 over r, then that will work, right? So the x and y in the other one, we could just, change one by a factor of 2 and the other one by 10, and things would work out. But now we're in a bit of a different category. The y is changing faster than the x in a way. So, okay. You don't need to know that. All right. So the terms are isometry and allometry. So the tree story would be, right, so we just scale up, the tree looks the same. And we're quite taken with this. I mean, when we look at the Earth, for example, right, we see river networks or geological structures, and that's why geologists have to put a hammer in there, or the graduate student, right, so for scale, so you can tell, because you can't tell if you take the right picture. They never found a graduate student. But anyway, okay, so dimension scale non-linearly, right? So as you go from small trees to big trees, and this is not what trees do, but as you go up through them, it might be that they become thinner, right? So even if as you sort of dilate by some amount here, it actually kind of stretches, and that can be connected to being a, well, we'll see why that might be. Yes.
I spent a lot of a while yesterday watching weightlifting videos of the smallest
Okay.
and the largest people, and there's definitely some allometry going on.
Oh, the different limb.
I mean, the tiny little people who are in the smallest weight class look very different than
Yeah.
the largest ones.
Yeah.
My boyfriend observed that the biggest guy seemed to have a way of helping the weight up using his tummy.
Yeah, no, that is a feature of the, yeah, right.
A big tummy thing that goes on.
Right. Yeah, because powerlifting is different to strongman, or and again from circus and the what's it called, the bodybuilding, right? Yeah, which are not particularly structurally strong. Yeah, yeah. So there is some. So this is a good point. So within a species, there is some amount of potentially some allometry or isometry. It depends on the species. It's harder because the scales aren't right. I mean, they're big for us. They're big changes, right? The little one and the big one. They're quite different sizes, but it's not orders of magnitude. Yeah. For whether something's isometric or yeah. So what you need, I mean, I'm just giving you 2 examples. So you can't do it from this. You would have to have the whole set of them going out, and you're measuring height and width, or say trunk width. You plot those things together, and we'll have these kind of plots. So you need a whole thing. This is just a terrible way of trying to show that it's not just a like a zoom on your camera, right? Like this. Yeah. So if you did that and it was allometric, it would squish. Yeah. Yeah, so isometric means everything scales, right? So length, height, and width are all proportional to each other as they get bigger, and you could say they're proportional to the mass of the tree, right? So you want to anchor it to something. So that's right. So so mass and volume, let's say they're proportional to each other, right? As we go up, then they'd all be to the power of a third, because length times width, yeah, good. So any deviation from that is allometry. Yeah. No. So enormous amounts of arguments about whether something is scaling allometrically, and if it is, like, what's the exponent, right? Just a huge amount of trouble over this, and it's the struggle of science to work it out. So there's the descriptive part where you need to get enough data, right? When we're talking about animals, it's tricky, right? Like you have to and I'll mention this a little bit, but if we're doing animals and how much energy they use, what are you going to do? You're going to get an elephant in on a treadmill and that's hard, right? So people have done this sort of thing, madness. Um, so or the other way is to figure out how much mitochondria they have, which is not such a great moment for the organism because you have to be reduced to, Anyway, so people are good at that part too. So it's differential growth rates, right? This word allometry, it became standard in, so it's Huxley and TCA, and I mentioned, it's actually, I have to correct myself, it was not, well, I mean, I would in general, but it's the Perkins I spoke about the other day is the son of the person for whom this building is named after. Right? Anyway, it's all tarred and tainted, and apparently will get changed eventually. Okay, we're trying to evolve. So Huxley, this is not Aldous Huxley. This is Julian Huxley, which is his younger brother, who was a eugenicist and wrote books with H.G. Wells, which you can find at Shelburne Farms in the library. And I remember coming across one. I'm like, it was Wells, and Huxley, and I'm like, oh, this could be interesting. And it was like evolution, the science of evolution or something. You read through, it's all about animals, and then the last couple of chapters are about humans, and it gets into, some good old-fashioned eugenics stuff. But as I understand, Brave New World was written in response to his brother and his colleagues at the time. It's like, this is not a great plan. Anyway, we go back and forth on this, obviously. But that's I think that's right. So, terminology of relative growth. I know it's just a little piece to say, look, this is something we measure all the time, and we should. I wonder if this will work. Oh yeah, that's the problem. It's Huxley. We're trying to. Okay, if anyone needs to escape, we've got a window open, and I've tried, but I got caught by this school jaguar about 17 miles away. So that, believe it or not, is a Ripping Yarns reference, and that is Michael Palin and Terry Jones. So this is the paper, yeah. Wow. This is Nature back in the day. This is 1936, yeah. And, oh yeah, so, this is Nature, just, publishing Nature things. Sulfur-containing pigments of plant origin, blah, 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 blah. Origin of the term solute, so a little bit of, language here, like sorting out language, it's important. Some bigger things, some little things, vitamins and plants, sounds good. And then some aspects of eugenics. Let's just rip out a little, wow. Anyway, okay. Same measure, other measure. So we're going to refer to, there's some nonlinear scaling. And, where something's dependent on one parameter is dependent on another. And then this kind of thing where they're both, we wouldn't want to say that one of them is dependent and we've got correlated measures. So the allometry talks about all of these things. So I like to show this. This is connected to the slides, I guess, that I'll eventually update to will have that, those visualizations of the biomass of life. And this is an old book now. Wow, it's almost 40 years old, but it was a science, I don't know, I just came across it. It's a Scientific American. McMahon is an important figure and same with Bonner and a lot of this allometry stuff for organisms. It was a Scientific American kind of coffee table book, actually. But, it's a nice one with real data. So, just trying to do this difficult thing of compare and think about how things change. Actually, snakes are pretty interesting, right? Because they're pretty much one-dimensional objects. So they have, if you think about cooling and those kinds of things, they're in a bit of a different category. Same with stingrays and so on, two-dimensional. All right. Always disappointing for the dinosaur people is that whales are the biggest things, so that's sad. They always have to just correct it a little bit. Trees, obviously, very big. That's in the background is the, yeah, the big unit. Must be a red, yeah. Okay, all right. And so we're down to sheep. These are quite small. And I think that's the biggest land mammal, yeah, the Balacotherium, right? So this is a pretty big unit, yeah. All right, things that can fly. So this would be the, I think, oh, it is an ostrich. Okay, so all right, and this unit is ridiculous, right? It's isn't it the lion's mane that lives under the Arctic and it seems like it's out of a Jules Verne story, but they're big things. Okay, so then you sort of move down and you have all these possibilities. Human hand. That egg there is from the yes. So this is from the largest egg. So this is from the elephant bird, which is gone, right? So that's from Madagascar. The kiwi. So of the struthious birds, right? The birds that decide like the flying is not for the birds. Was sort of disappointingly gave up on it. The kiwi has, I think it gets to a state where the egg is a third the size of the bird, which is a pretty impressive achievement of evolution. Anyway, so, but that's the biggest egg. But of course we don't have it anymore. And then you get down to small and small things. All right, so these are lots of ranges of life. There's a flea, which is a nasty little thing, and that's the flea's arm here. So small and smaller and smaller, and it's kind of remarkable what we get down to. And we get to things like viruses and so on, and they're little living algorithmic objects. So you start to think about, well, how do these things fit together? And so these are this is in grams, right? So this is pretty remarkable. I mean, there's 21 orders of magnitude here in terms of that's in terms of mass, right? So if we start to think about dimensions and we roughly say isometry, which may or may not be right, but we roughly say isometry, then we have to take the cube root of that, right? So there's sort of 4 orders of magnitude with respect to length scales, right? Typical length scales. So length scales will matter for when we start to look at what organisms can do as a function of size. So that becomes the big piece, right? What's the mass of, well, it's taken to be the primary measure. What's the mass? And then what are the properties? So for mammals, there are things like, well, we'll get to it. But mass is sort of the anchor. Okay, so this is the number of cells. Just how many different pieces, how many different cells do these systems, these things that run around by themselves have? And we start with 1, and it doesn't go out a long way, right? At least according to this, 100 different cells, which, from a chemistry point of view, and or a Lego building point of view, and I'll have this in another set of slides. We are made out of remarkably few things, and of course, if you go to the elements, even less. And then if you think quarks are real, then it's just some up quarks and down quarks and some other mush, which is not a lot. That's a difficult thing to put together. But yeah, so we're still at pretty basic stuff here, and sequoias here and whales out here. So that's it's just a very interesting thing to think about. How many different bits do you need, and why would whales need more than us if they do? So scaling within organisms. So this is growth of a person. We're fine with babies, right? This is how we keep having them. Well, it's complicated, but we sort of look after them and we think they're cute and so on. But if one walked in, was my height, it would be extremely disturbing, right? This is not right. This is not right. It's just not right. So it sort of connects to your weightlifter thing. The head is, so there's a scaling that happens as you grow, and things get to be somewhat reasonable by the end of it. Right, so don't rescale babies. That would be we'd be upset about it. So this is some of the allometry type stuff. So this is body height, and then arm length. This is a measurement of it. You can see it's not a lot of orders of magnitude. This is 1 order of magnitude here. Humans aren't that tall. This kind of thing happens a lot in a lot of systems where there's a crossover crossover in scaling. So you may have two regimes. This regime is based, there's 2 points, so it's not great. But the claim is that, and this is, I mean, it's clearly something that's happening. Your arms are kind of catching up. So the framing here is that there's allometric scaling early on, and then you start to grow isometrically, right? But you got to get the brain bit in place and right. Because of all that great smartness that we have as humans. I tweeted something yesterday, which was, we're in September, right? Which is, in honor of 7. It's of course the 9th month of the year, and it's because Julius and August or whoever wanted to make them, even more famous. So, pretty good branding. Get your name on a day of the week if you're a god or something. But naming things after people. Anyway, so here we are in month 7, but 9. So it's kind of embarrassing. Of course, it was mansplained to me that Julius anyway. I'm like, okay, guys. We know what happened, but we could have shifted the index up a little bit. Okay, so so there's a crossover in scaling. So these are difficult things to measure. This is the one that's in your assignment. I just want you to go to Wikipedia there. I mean, this is not a hidden thing as to who's lifted the large. This is from a long time ago. The doping and the cheating and all that stuff. That's complicated. That would be interesting. In cycling, this is done, right? So that it'll be tracked like how fast someone's going up a hill or whatever, and look at the wattage and whether that's humanly possible or human plus funny ingredients possible. Okay. So, and I mentioned this the other day. It's like the idea. It's the cross-sectional area, and then within that, and to the degree that people across those weight ranges are isometric, right? That's sort of what's being presumed there, and then it's being presumed that it's like the cross section of some part, everything, the torso, that makes it possible. But if they do have extra features like a tummy, it's a different, they're doing some slightly different things, right? So does the tummy help these ones? But obviously they lift a larger amount, but if you divide out this best fit, in this one you can see this one's just above the line, right? Right. So this would be the normalized by weight class, the strongest. Lots of stuff to do with speed and for humans and then across organisms. So I have this little section. Yeah, good. So these are fun. This is and they tend to appear in Nature and Science. People love these papers. How am I doing for? Well, just volume, not quality. Not asking about that. Okay. I grew up in a family of 3 boys, and everyone yelled all the time. Anyone who ever came to visit us in the farm, which was difficult, was shocked, and it was just completely normal. But the thing was, if someone was too loud, someone would say, "I'm not in the next paddock," right? Because you call fields paddocks. That's just a standard word. I'm not in the next paddock. Lots of swearing. If you've ever seen Trailer Park Boys, it is Trailer Park Boys. That's what I grew up with. So if we want to have a swear off. Yes, it's all baked in. So, I should say, this is a clean space. We don't have those things. All right. Okay. Somehow I can stop it. Let's see. But it is my native language. So this is speed as a function of time. So what's going on here is different races, right? So the longer a race takes, the slower the average speed, which makes sense. But you can see, again, there's this kind of break in scaling. It's a little, there's not, again, many orders of magnitude, a little bit better. I mean, maybe we've got a couple orders of magnitude, bit of a stretch. But let's see, this is, running is A and B. So this is running, and then this is swimming. And they're world record times. So what seems to happen is around about 150 seconds, is it? Yeah, 150, 170. So the average speed is decaying as time it takes, so some power, and that there are 2 exponents. There's one here for the sprint type pieces, and then out here for the longer ones. And if you're familiar with track and field, like 800, the 800 is where you start to have some strategy, right? The 400, what is the thing for the 400? It's just push. I heard it the other day. It was push. there's another P, and then there's power for the third, and then there's prey, right? So it's just, because you're just gunning it the whole time. Whereas the 800, you can have some strategy. You can start to mess around a little bit. It's hard to hold that. And then certainly the 1500 starts to be much more strategy because it's hard to burn off the whole time. If you want to set the world record, you have to hold a constant pace pretty much. That's well understood, but at most distances. But so it's really kind of clear. There's a little bit of a break, and it's true even for swimming. So we're burning off, this is anaerobic aerobic transition. You kind of have a couple of minutes of stuff just sitting in there if you need to go really hard, and then it's gone and you're kind of bumped. So if it's running, it's about a 1K. So it's a little bit further than 800. And this really comes out in the physiques of people, right? The 800-meter runners look like long distance. Generally, they're a bit stronger maybe, but they start to look like marathon runners. Okay, I know this is exciting for you. Yes?
So when you say each small scaling regimes, that's because the number of magnitudes under each
yeah. Yeah, so this one's 1 order of magnitude. This is not even 1 order of magnitude. You're trying to make a little kink there. Right? Because if you decide yourself, there are 2 scalings, then you have to also find that break point. And again, these really do appear in the world. These are very natural things that happen in lots of different systems. There's a break. I think you see it in earthquakes because of, maybe I have it here, because of the thickness of the Earth's crust, right? So there's some characteristic scale. Like if this is true, you want to be able to explain. If there's a break, you want to explain what's happening at that break. This doesn't tell you why this. There are betas here, right? This is a minus. Why these exponents are what they are. Wow, they're pretty weak. But you want to be able to sort of say, there's something. Point to why there's something happening there. This is when was that other one was 2000? That's 2000. This is 2004. I don't know. Nature and Science. Oh my God. Anyway, so this one is a linear extrapolation for the fastest time, right? In 100, right? So no one, of course, there was Bolt who set all these records. Different shape. He was a surprising shape, right? No one thought he should be a 100-meter runner. He's too tall. It'd take too long to get going. Yeah. Yeah. So this is, I know it's sort of funny, but it was terrible because they did a linear extrapolation. Right. So here's 1900, here's 1980, and they've taken the fastest times at the Olympics. So that's why it's going up and down. It's not the world record. Right. So world record is going dick, 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 dropping. These are the fastest times. Linear extrapolation, this is men and this is women. So their point is in 21:56, women will run faster than men. Of course, there is a problematic point out here where, it's 0. So anyway, good for them. But this is a linear fit, So on the other hand, we could have kind of come up against reality, right? Which is there's only so fast you can run. We've got some funny shoes these days. That's helped. And we put the funny things in ourselves, the juices, so that helps as well. But mechanically, there's still some limit. Anyway, so, good for him. Cheeky. How are we doing here? 11:05. All right, it's good. So people like to play around with these things. All right, we'll go away from humans a little bit, maybe more organisms. This is, again, to show something that's a little questionable, but as you go up through organisms with horns, right, they sort of grow a little bit, but you can see there's barely anything here. And this is the length of the skull and the horn length, and they're trying to get a power of 4 out of it, right? And you'd have to explain it. You'd have to give you 4, but this book is full of like, okay, maybe. I know one person has been in the second part of Puck's has seen this, but so here's an example where people argue forever about which exponent is which and right? So this is to do with, this is incredibly important if we think about life, because in ecology and how the whole thing fits together, because this is this basic story of you've got an organism that's just hanging in there, right? Just its basal, what's its basal energy? Just to keep running. We're not going as fast as we can. I'll have some scaling about that in a second. This is just hanging around. You're a sheep eating some grass, whatever. You're a human watching TV. What's That's a funny data set actually. Like people have measured humans doing all sorts of things, right? Running whatever, and like what is the energy expenditure for lying down and watching TV, and then lying down and watching TV, and then lying down. They're all different things. Right? There are like tables of these things. Great. Okay, so basal metabolic rate, right? And then we have some body mass, and we're going from this is a shrew, so pretty small. These are on the order of 3 or 4 grams, right? Hanging in there. You know, vertebrates, right? We got the whole deal in here, the same plan. We look the same basically to start with, which is crazy. And elephants, so is maybe 6 orders of magnitude. There's the elephant shrew, which is very confused about. It's just, I don't know how that happened. Humans like to, yeah. Anyway, so there's a prefactor, and that's going to depend on, that's claimed to depend on body mass. So I'm giving you some things that are claims. So we've got this scaling, and it's some power of alpha, and if you looked on a log-log plot, the C moves it up, right? So if you increase C, it moves it up. You take the log of this, you get a log 10 of C, and then this alpha log 10 of M. So there's a linear part for the log 10 of M, and the C is just a vertical offset. So as it goes up, we go through, the claim is, through monotremes, marsupials, eutherian mammals, and birds. So birds have got a big job, right? They're flying. It's a pretty impressive bit of being an organism. So they run at a slightly higher temperature than our team. This is the placental mammals. Marsupials you outsource the situation into a pouch, right? So there's sort of the idea is this is to do with, how the young are carried and how it all works out. And then monotremes, of which we have 2, the excellent platypus, who will appear on a pendulum soon, and the echidna, a couple of types of echidnas, so that's Australia's porcupine. These ones, they lay eggs, right? They lay eggs, which is just well done, nature. Yeah. So monotremes. So they seem to run at a bit of a lower temperature. A lot going on with these guys. They've got electromagnetic sensing, got the poison in the back legs, the beak, the fur, the cuteness. You can pat them like, oh, I should find that. That feels important. Patting platypuses. Very hard to see. My grandmother said she saw one in the wild once. Oh. I can't find it. They are pretty small, yeah. Oh, here we go. Let's see. Come on. Ooh, it's friendly. Oh. This is kind of amazing to me. Yeah. Like a messed up dog. I really had no idea you could do this. I mean, they consider, you don't touch, you leave them alone. Oh, what a champ. Anyway, so you can spend the rest of the day looking at platypus videos. Whereas koalas will idiotically bite you or something. These guys are obviously, a bit smarter with their little brain in here. But excellent fur, yeah, cool. Really good organisms. Okay, so you'd think it'd be 2/3 because you'd say, okay, you're sitting there, you're balancing heat loss. We're all spheres, right? We're just spheres, right? We'll do the physics thing, but not really. We're some objects that are scaling. And then, so you'd say surface area is the problem, and surface area would scale as volume to the 2/3, right? So this is like length squared, volume is cube, length cube, so that's the transition, right? If you just want to think of a sphere, right? So 4 pi r squared for the surface area, 4/3 pi r cubed for the volume. So lots of, straightforward, you think about these things quickly, and then you say it's mass to the 2/3, right? Density is not changing too much. So that's isometric scaling. That's a reasonable thing. It's what people thought in the past. You'd think maybe there's some log normal fluctuations, right? There's going to be some different things. There are, like, what is it? Alaskan ground squirrel can have its blood below 0 Celsius because it has supercooled, has some sort of antifreeze situation, which is impressive. And then there's, if we want to pull out the whole physics box, is the Stefan Boltzmann law, this is the black body radiation thing. You don't have to worry, there's too much solve the ultraviolet catastrophe, which is, yeah, basically the energy loss from a black box, which we are a little bit, is proportional to S and then the temperature, right? There's an exchange that's going on. And this is why, if you're running around at night, someone can find you with goggles, right? Because you're giving off infrared. We have other ways of cooling down. Depends on the organism, right? We sweat. Horses sweat. Dogs decide to go straight up the tongue, which is charming, but kind of a lot, Cats don't ever do anything, right? So they've got it, They're too smart to, Actually, Pratchett just loves the heat. He just wants to, if it's hot, he'll just go outside and boil himself. So anyway, this is what has been known for a long time, and it's in the next semester where I go through it all because it is an unbelievable disaster. It's supposed to be 3/4, so it would be faster, right? Scaling faster with mass, so that energy usage to keep an organism running. So, okay, that's plausible. Maybe it's harder because of networks, and you've got to keep this thing running. You've got a heart in the middle and going out to all these little sinks. The capillaries or capillaries, I know one of them is right. I had a student wince when I said the other one. Anyway, so I know it can be painful. But that's a great network problem, right? You've got and you can think of cities being similar if everyone has to commute in. But now we live in remote worlds, perhaps. So that's a bit strange. So it's higher than you'd think. So there's some sort of inefficiency or something that's different from physics. They're sort of running hotter than they have to be. And then there's a bunch of other things that have claimed, right? So, and that original 3/4 comes from a study of 11 animals in 1930, and it was to do with figuring out how much to feed your livestock based on their size. Rather charmingly, if you go back in the 1800s, people thought it was 2/3, and that was first came up with by some physicists who were trying to help out a tobacco plantation who wanted to know how much to feed their workers based on their size. Yeah, we've come so far since then. Yes. Anyway. Well, we put Jeff Bezos into space, didn't we? Okay, so he came back, which is a real shame. So 3/4, right? So we've got more of these pieces. That's not keeping up with your overall mass. So that does seem to be true, even if this is not 3/4. You're getting bigger and bigger. You've got an elephant, but it's not quite being populated enough with these little, these are the little energy stations, right? The blood comes through, lets out some, material through diffusion. So they're getting more and more sparse. This is a claim, right? Reproductive maturity that scales that way. Heart rate decreases, and these are all the trends are true, right? So mouse's heart goes, and then when you get out to elephants, it's much slower. Population density also rough, but if you go back to the original paper for this and take out a couple of things that the author said were wrong, you get 2/3. It's just a debacle. What happened was the 3/4 thing took hold and everyone found it everywhere, and a good sort of following of other people's behavior that humans are good at, even this sort of thing. If you put these two pieces together, let's just not leave the 3/4 thing aside, then average heart rate, right, so obviously varies, but it's decaying with size. It's lower, as I said, for bigger organisms. Bigger organisms tend to live longer. Of course, you have some birds that have been around for since your great-great-grandparents, and they swear in like the 1800s or something, which is remarkable. And tortoises can live for an incredible amount of time. But this is, let's say, let's just take them as is, and we can just leave the beta aside. Then let's multiply them together, right? So the average number of heartbeats in a lifespan is m to the 0. So and there's estimates that it's about 1.5 billion heartbeats. Right? This is where you get people saying you shouldn't exercise because you're using them up too much, or you have a battery. I think there was some important person who said that they felt like you have a battery. Okay, whatever. People have funny ideas about these things. But this is not entirely wrong, right? It's even whatever this scaling is. But this is sort of, if you run out the clock, so to speak, for how long you might live. That's about true. So, yeah, so a mouse is running along, the ticker is going faster. So, but there, we have a clock, right? But their internal clock is sort of, if you scale it out, I don't know what their perception is like, their sense of time passing. But they get a an elephant and a mouse kind of match up a little bit. All right, so that's a bit of a mess, and it's grown into this thing called the Church of Porterology. So that's a 3 and a 4 is the silliness there. All right, how are we doing? Okay, one more piece here, just on organisms, trying to see how they fit together. This is debated. If you look at the original paper, it's pretty messy, but this is number of species on islands, the number of distinct species. And so this kind of idea, this is the number of types, right? So if we think about language, we think about the words in a dictionary, they're the types. And then the tokens are the ones that appear in a book. And same with organisms, there's very general systems language. These are types, and then there's the actual organisms, right? So lots of ants, and each one of those is a token. Anyway, so the number of distinct species, or the number of distinct, it's interesting. It sort of connects a little bit to, how the number of distinct words grows as you read through a book. Okay, so that's called Heap's law. I should write that down. So this is a claim. It's a bit weak, right? So power of 1/4. I don't know if I can get this paper to. I know, I'm running out of time. Let's see, where's the number of species? So they fit they fit a line through this and said it's 1/4. That's what you've got. This one, pretty messy. It's not really, clearly not doing it. There's sort of this hypothetical 1/4 thing. God, what a mess. All right. So you go back, but this becomes gospel, and then people, create theories for it, and it's all true. I'll just show a couple more, and then we'll get to come back to some more biology things, I think. But so this is a very dire thing for us as humans, and for organisms is cancer. And so this is I don't think anyone's figured this out. This has been sitting there for a few years, and it's something. If you have a clever idea for how this might work. Okay, so what this plot is, so these are different types of cancers. This is the lifetime risk of them. So this is for people. And this is the total stem cell division for that particular region of the body, right? So lungs, for example, are here. So this is the number of stem cell divisions that you might expect. So this could be turned into rates, if you like, but it would just still be the same thing. If you roughly put a line through this, it's about 2/3, right? So there is, and so this is why we have the Delta variant, right? I mean, because we've had a virus sitting inside of us, like dig, 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 and it makes mistakes and whatever, and then one of them is better. Let me just quickly, and so this 2/3 means that it's rolling over, so that, if you have a region of the body that is replacing, it's turning over faster and faster. It's not a simple rescaling, right? It's actually doing better in a sense if you normalize it in the right way. It's doing better than something that has lower turnover. Of course, we have all these little contraptions in us, and the framing for this is, we don't fall apart, right? And we've got a lot of little things there are little things collapsing inside of us all the time that are being repaired. Engineered systems don't always, it's hard for us to do that for engineered systems. We have to kind of really, it's not a natural thing to do. You want something to be just robust, but through evolution, we've got all, DNA errors all the time or whatever, and they're all being repaired. So we build all these evolution built all these contraptions to repair everything, and it's just accepted. There's colon cancer in one side of my family that wiped out lots of people in different, quite young, some of them. And my mother was the one that finally found to have, what it was, and it's there's just a little repair switch that's just not there. So it's not, there's a little repair machine doesn't exist, and so that leads to this. It's an incredible understanding and potentially fixable. Whales, it seems, don't get as much cancer as us, right? So they seem to evolve to a point where they have lots of fixer-uppers. I don't know, maybe that's not quite true, but, we're living longer than we used to, so we're getting into maybe some trouble. Yes?
Well, one thing one can say about that chart is it's a refutation of the earlier scaling by heart rate, which is to say the parts of the body do not age at the same rate.
Well, that's, yes. the lifespan thing there was to reproduction age. Yeah, so this part is a, yeah, right.
But
right.
essentially, it's not, I mean, heart rate is nothing, I mean, different, die of all kinds of different things having to do with different systems collapsing.
Oh, yeah, 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 yeah. Yeah.
These are, this is showing
Yeah.
some of the, the differences in how they do the collapse.
So I'll say it's connected. So there's the, not everyone likes Jared Diamond's Guns, Germs, and Steel, but he has a principle in there which I think he came up with is the Anna Karenina principle, which is it's from the quote, and I'll finish quickly. It's the quote at the start of which one? No. Why have I got this? Yeah. So it's a quote at the start of Anna Karenina, and it's translated in English in various ways, but happy families are all the same, and unhappy families are unhappy in their own special ways, right? And this maps out in a lot of different ways. And when it comes to systems, there are lots of ways for things to fall apart. And it's also mapped, I think, into our emotions, right? We have lots of negative emotions: anger, disgust, sadness, fear. We have because they all matter, right? That when something is bad, you need a fine-grained kind of way of sorting it out. And then happiness is just yay. Last thing I want to say is here's lung for non-smokers and smokers, right? So there is a big difference if you do something environmentally to yourself. That's this is a order of magnitude, actually, really. It's a huge increase. So there are a few pieces like that. But in general, there's luck. All right, so why is it 2/3? All right, it's a good place to stop. Thank you, people. We'll be back here on Tuesday. Those of you who want to come back.